notation we call phi kk. So this is the notation for partial ACF. So ACF is rho k. Partial ACF is phi kk. So we start with, so phi 0, 0 is always 1. This is by definition. So this is by definition always 1. And then phi 1, 1 by definition is always rho 1. Okay, so phi 0, 0, 1, phi 1, 1, rho 1. So that's by definition. And for any k larger than equals 2, so we can calculate the phi kk here. So that's the correlation between yt minus k. But we removed a linear combination here. Or you can say this is the regression of yt on, say, the variable between yt minus k, which is yt minus 1 to yt minus k minus 1. So you have yt here. In yt minus k, the variable between these two, so that is yt minus 1 here, yt minus 1, and the one before yt minus k, that's yt minus k minus 1. So this one here is the regression of yt on yt minus 1 to yt minus k minus 1. And this one here is the regression of yt minus k on, say, yt minus k minus 1 into yt minus 1. See the coefficient. Beta 1 is the coefficient for yt minus 1 here. So beta 1 is the coefficient for yt minus k minus 1, the one close to the yt minus k. So rho 1 is for yt minus 1 for the regression of yt, and rho 1 is for yt minus k minus 1 for the regression of yt minus k. But rho 1, beta 1 here, beta 1 here, so the beta 1, so they are same. Beta 2, same. Beta k minus 1, they all same. So this is a definition. And then how, see, you have beta 1 to beta k minus 1. Then how do you know, right? So what the values they are. So we want to choose those beta values to minimize. So we call this, you can call this some square error, something like that. So this is yt minus this one here, the regression of yt, yt minus 1 to yt minus k minus 1. So yt minus is like prediction and then take square, right? Like a sum of square errors. So we minimize this expectation and then found the betas. Okay, so let's do example here. So find the partial ACF for AR1, causal AR1. So causal AR1, different equation. And we're given, so phi absolute value is less than 1. So this is AR1, causal AR1. So by definition, we know phi 0, 0 is 1. And phi 1, 1 equals rho 1. For AR1, rho 1 just the AR coefficient phi. Okay. And phi 2, 2, so phi 2, 2 is the correlation between yt minus 2, right? And here we need to remove the variable between, so that's yt minus 1 minus beta yt minus 1. We just have one beta, so we skip the subscript. Okay, that's yt minus 1. Okay, so we need to find this beta here. Then we minimize, see, yt minus regression of yt on yt minus 1. So minus beta yt minus 1 take square, take expectation. So expectation of the square, so we multiply out the square. So that's yt square minus 2 beta yt minus 1 and plus square of beta yt minus 1. So the first term, expectation of yt square. So what is expectation of yt square? Okay, so for this AR1, expectation yt is 0, right? If you have variable x and its mean value is 0, what is variance of x? So variance of x equals expectation of x squared minus expectation of x n squared. So the first term, you take a square first, then expectation. Second term, so you take expectation first and then square. Okay, so if the mean is 0, so this term is 0, right? For a variable with mean 0, so variance of x, just expectation of x squared. So we have expectation of yt squared because mean of yt is 0. So this term just variance of yt. So variance of yt is, because yt is stationary, we call this gamma 0, right? And minus 2 beta expectation. So this term here is we take expectation. Expectation of yt minus 1. Okay, so now we continue here. If mean is 0 here, so you have two variables, both mean 0. If mean equals mean of y equals 0, and then the covariance between x and y. So by definition, this is expectation of product xy minus expectation of x times expectation of y. This is a definition. So mean 0 covariance between x, y is just the expectation of the product. So here we have expectation of yt, that's t minus 1. yt minus 1, so both mean 0, right? So this one is the covariance between, so this is covariance between yt minus 1. So we call it gamma 1. So this is the gamma 1. So last term, so beta 0, okay, beta squared times expectation yt minus 1 squared. So the same as this, because yt is stationary, so that's gamma 0, right? Okay, so now we want to minimize this equation right here to find beta. So we take derivative right here with respect to beta, and then set equals 0. So the derivative, the first one here is a constant, right? So there's no beta here. And the second term is negative 2 gamma 1, and we take derivative of beta with respect to beta, so which is 1 here, plus gamma 0, so coefficient, so beta squared, take derivative, so that's 2 beta. So we have negative 2 gamma 1 plus 2 gamma 0 beta equals 0. And then we solve for beta. So beta equals gamma 1 divided by gamma 0. So see, we have beta just rho 1. And for AR1, rho 1 just phi. Okay, so now we can calculate phi to 2. So phi to 2 is the correlation between yt minus 2 with this linear combination removed from both variable. Okay, we plug in beta. So beta is phi, right? Rho 1 phi. So phi yt minus 1, and here to see the same here. And we just calculate this correlation by definition. So the numerator just a covariance. The denominator is square root of variance first variable, square root of variance second variable. So this one on the top, because it is uncorrelated with past values of yt, no correlation, so the numerator is 0, so the whole thing is 0. So phi to 2 equals 0. So you can follow this process and calculate for any k larger than 2. So phi kk is 0. Okay, so this theorem here, so this is important here. Okay, first of all, you have ARP, right? So you have ARP, and also this ARP must be causal. You have a causal ARP, and then phi kk equals 0 for all k larger than p. So phi kk equals 0 for all k larger than p, and phi pp, the last one, equals phi p. Okay, so in ARP, you have p coefficient, p1, that's for yt minus 1, right? And then you have phi p yt minus p plus y noise. So, and you can calculate phi kk, so like I said, phi 0, 0 is always 1 by definition, and phi 1, 1 equals rho 1. You can calculate the rho 1 from this ARP, and then calculate phi 2, and phi pp. So we know if you have ARP, this is not 0. And we also know this is phi p. This phi p is from here, the coefficient for yt minus p. This one is not 0. So phi pp equals phi p. And then you calculate next one, say p plus 1, p plus 1. Okay, that's p plus 1. So this must be 0. So this is a 0 and everything else, so that's a 0. So if you have causal ARP, so ARP causal ARP, and then the phi kk, the partial ACF is 0 for k larger than p. And then partial ACF, I like a p, so that's just coefficient for YT minus P. Question so far? Okay, so let's do one more example, and then I will show you how to do the partial ACF in R. So partial ACF for MA1. So you have a invertible MA1. So here, invertible means theta absolute value less than 1, right? Okay, phi 0, 0 is 1, phi 1, 1 equals rho 1. Rho 1, oh, sorry, so phi 1 equals rho 1. And for MA1, rho 1 is theta divided by 1 plus theta squared. It's not phi, sorry. This is phi, theta divided by 1 plus theta squared. That's rho 1 for MA1. So now we calculate phi, okay, phi 2, 2. Phi 2, 2 is the correlation between YT minus beta YT minus 1, YT minus 2 minus beta YT minus 1, right? So we still need to choose the beta value here. So we minimize this function. So we did this before, and we take derivative, set equals 0. So beta is rho 1. And for MA1, this is the equation for rho 1. Okay, so we plug in this in to the formula to calculate phi 2, 2. So correlation between YT minus 2, but we remove the linear combination between YT minus 1, between YT minus 2, we just have one YT minus 1, right? So this is rho 1, this is rho 1 here. And then we have numerator, so covariance between YT minus rho 1, YT minus 1, YT minus 2 minus rho 1, YT minus 1. Okay, so now what do we have here? So YT minus 2, the covariance is gamma 2, right? And YT minus 1, covariance is gamma 1. And we have coefficient negative beta 1. So we have, okay, gamma 2, the first one, and minus beta, rho 1, gamma 1. And then this one here, YT minus 1, YT minus 2, covariance is gamma 1, right? Because the time difference is 1. So that's gamma 1. And coefficient negative beta 1, gamma 1. And the last one is negative beta 1, YT minus 1, negative beta 1, YT minus 1. So that's covariance YT minus 1. Covariance YT minus 1, that's gamma 0, right? Negative rho 1 times negative rho 1. So that's rho 1 squared. And variance of YT minus 1, that's gamma 0. So this is the numerator. Denominator. So denominator, we have this one. So we calculate this one first. Okay, variance of YT minus rho 1, YT minus 1 equals variance of YT, the first one, and plus negative rho 1 square variance of YT minus 1. And YT minus 1 are correlated, so we subtract negative 2 beta 1. row 1. So that's plus 2 times negative row 1. And covariance between yt minus 1. So this equals the first term is gamma 0. And negative row 1 square, so that's row 1 square. Variance yt minus 1, same, because stationary time series variance is a constant, right? Minus 2 row 1, so this is a gamma 1. So we have gamma 0 plus row 1 square gamma 0 minus 2 row 1 gamma 1. So this is the one in here. Row 1, yes, this one minus 2 row 1, yes, this one here. So that's the first term. You have square root of this. And second term here, so this is the same. So the first variance of yt minus 2, that's gamma 0, plus negative row 1 yt minus 1 square variance. So that's row 1 square and gamma 0. And minus 2 row 1 covariance between yt minus 2, yt minus 1, that's gamma 1. So the two variances are here are the same, right? And then the same here. So we have square root, we have another square root of the same thing here. So we can remove the square root here. So the denominator just gamma 0. So this is just the denominator. And then we divide it by gamma 0 on the top and bottom. So the first one, gamma 2 divided by gamma 0, that's row 2. And 2 row 1, so gamma 1 divided by gamma 0 is another row 1, so that's row 1 square. And this one just a row 1 square. Denominator gamma 0 divided by gamma 0, that's 1 minus 2 row 1, gamma 1 divided by gamma 0, another row 1. And then this term just row 1 square. So we have for MA1 row 2 equals 0 here. Negative 2 plus 1 row 1 square, so the negative row 1 square. So denominator is 1 minus row 1 square. So and plug in, so we have row 1 equals theta divided by 1 plus theta square, right? So plug in here. So this is the phi2. So partial ACF, I like to for MA1. And then so similarly, you can calculate phi kk for k larger than 2. Okay, so here is the formula. And we know this is not 0. So ARP, well, we just do AR1 because we did example for AR1 and MA1, right? So ACF for AR1, okay, it's not 0. Partial ACF, row 1, 1 is not 0, but for all row KK, K larger than equals 2, this is 0. Oh, sorry, this is equals 0, equals 0. Now for MA1, we know the row K is not 0. Row K, okay, row 1. Row 1 is not 0. Row K is 0 for K larger than or equals 2. But partial ACF V11, so that's not 0. Let me do this one. VKK, everything is not 0. So you see the pattern, right? So we call this, for if you have ARP, you have MAQ here. ACF, see, no 0, nothing is 0 here, right? We call this a tails off. And for MA1, partially ACF, everything's not 0, we call this is tails off. In ACF for MA, no ACF beyond leg Q, right? So we call this cut off after leg Q. And partial ACF for ARP, so the cut off after leg P. So that's for ARMA. So now we can see, so partial ACF is to ARs as ACF is to MAs. So this is the reason we create a, right here, concept or definition partial ACF. And for ARMA model, so for ARMA model, rho K not 0, phi KK not 0, so we call this tails off, tails off. So this means if I give you time series YT, you plot ACF and partial ACF both, right? You plot both ACF and partial ACF. If you see, so ACF tails off, partial ACF cuts off after like some like K. And then this is, you have a ARP model, right? So if after like P, you have ARP. So for the ACF, if you have ACF cuts off after like a Q, and then partial ACF tails off, this gives you MAQ model. If both ACF, partial ACF tail off, that is ARMA PQ. So, and for ARMA PQ, what is P, what is Q? We have no idea. So it means it's not clear. We cannot tell the value of P or Q from just ACF or partial ACF plot. So we'll learn how to determine P and Q in next unit. So next unit we do parameter estimation, model selection, model diagnostics, and for ARMA models. Okay. So, and one more thing for the partial ACF. Suppose you have a Gaussian time series. So YT is normally distributed, and then phi KK. So there's a equivalent definition for partial ACF. So phi KK is just a correlation between YT minus K, given the variables between YT minus K. So this definition and then the definition we used before, they are equivalent. Any questions? So let's do a R. So we use library TSA. So the first example, we have AR1 and phi is 0.9. And AR1.S is a simulated time series AR1 simulated AR1